Hi, in today's video on counting, I'll be going through the Pigeonhole Principle. The Pigeonhole Principle is a principle that we've been using since we are young and it has been drilled into us intuitively. While it's easy to state intuitively, it is hard to apply in mathematical problems. And we'll go through examples to show why is it hard to apply. But first, let's state the Pigeonhole Principle. The Pigeonhole Principle states that if you have at least kn plus 1 objects distributed among n boxes, one of the boxes must have at least k plus 1 objects. Take for example, you have 3 boxes. Now you have 3 boxes and 4 objects. And so, it states that one of these boxes must have at least 2 objects. So why is that so? Well, these 4 objects can be placed one object, one into each box. But you still have one more object left and these have no choice but to go into one of the other boxes. And so, one of the boxes must have at least 2 objects. And this is basically it for the Pigeonhole Principle. While it seems like common sense, it is actually very hard to apply in real life and it takes a lot of practice to understand what are the boxes and what are the objects. The generalized Pigeonhole Principle over here is just a reformulation of the same thing as the Pigeonhole Principle. But in this case, you are able to see one box have how many objects at least. But let's take note that while the Pigeonhole Principle states that at least one of the boxes must have n plus 1 objects, it might be so that some of the boxes have no objects and the other boxes have even more than n plus 1 objects. So you are not able to tell how many boxes are filled with how many objects, but you at least know that one of the boxes must have at least n plus 1 objects. I'm going to say this example, which is using the same example, 3 boxes and 4 objects. It is possible to place all 4 objects into one box. It still fulfills the conclusion that at least one of the boxes have 2 objects, in which case it's box 1, but the other 2 boxes are 0. It is just that in the worst case scenario, when all the boxes are filled already with the minimum number of objects, one of them, because the objects exceed the boxes, must be placed, have additional objects to be placed with. And so, this is basically it for the Pigeonhole Principle. Let's look at some examples to see how hard it is. Now, we want to show that any set of 10 points chosen from a square whose side length is 3 units, 2 of the points must have distance at most square root 2 apart. And why is this so? Well, we can split our squares into 9 subsquares and each of these subsquares have length 1 unit. In this case, we just place 9 of the points inside this square. So we can place them like this. And because there are 10 points, one of these points must lie inside the same square as the other 9 of the points. And so 2 of these points lie in the same square. And what's the furthest we can put them apart? Well, we can put them at the diagonals here and here. And what is the distance between them? The distance between them is just square root of 1 squared plus 1 squared, which is just square root 2. And this proves and shows what we want to show. But why do I say it's hard to use then? Well, one wrong approach will be to split your square into rows. So you have 9 rows in this case. In this case, you can put your points anywhere along the row. And then you realize that one of the rows will have of course 2 points. But this point could be just lying at the 2 ends. And so, the distance between them is 3 units. And you can't show that there must be 2 points that is at most square root 2 apart. Hence, this is one way to show that if you do not cut your original problem into smaller subsets so that you can fulfill what the question wants, it is difficult to apply the pigeonhole principle correctly to get to your conclusion. Now, we shall see how the pigeonhole principle is used in graph theory, and this problem is called the Ramsey type of problem. So one of these problems in the Ramsey type of problem, a specific one, is that if you have a gathering of 6 people, and these 6 people can either know each other or don't know each other, at least 3 of them either are all friends with each other, or at least 3 of them are complete strangers to one another. And let's start with some notations to understand what am I trying to say to help us solve this problem. The first is we'll treat these people as vertices, and then we'll just draw edges to all these people. So in this case, not all the edges is drawn, but imagine everyone is linked to one another. And this will be known as a clique. So a clique is just a set of vertices with edges joining all pairs of the vertex. In our case just now, with the 6 people, it just means a 6 clique. And then, within the 6 clique, you can color the edges either blue or red. And so you can color the edges blue or red. And basically, a Ramsey number is just the smallest size of the graph, or the smallest clique size, such that at least a blue P clique or a red Q clique is there. And so if we prove this, it just means that 6 people are required to form at least either a blue 3 clique or a red 3 clique, where in this case we can label blue as the people who know each other and red as the people who do not know each other. And by proving this theorem, it shows that this Ramsey number exists. But we can do better. From the extension of this problem, Ramsey showed that for any 2 integers, this Ramsey number always exists as long as the integers are larger or equal to 2. The proof can be found online, but instead we will now show that it is bounded between 2 other Ramsey numbers. What do I mean? Well, it means that the RPQ is always less than or equals to the RP minus 1Q plus the RP comma Q minus 1. And let's just prove this to show the boundedness. The existence, like I said, you can search it online, and it's just proven using mathematical induction. So, we want to prove that the Ramsey number is always smaller than this number. And since the Ramsey number is the smallest number for a clique to have at least a P or Q subclique in the respective colors, we just need to show that this number fulfills that condition, that there will be at least a P blue clique or Q red clique. So we let n equals to this number and consider this clique, n clique. We fix a vertex V inside this n clique. So for example, this is the vertex V. The number of edges incident to V will be n minus 1, because there are n minus 1 other vertex points, and each will have a edge connecting it to V. And so the total number of edges incident to V now will be R bracket P minus 1 comma Q clique plus R bracket P comma Q minus 1 minus 1. And then, by the generalized Pigeonhole principle, we know that R bracket P minus 1 comma Q blue edges must be possible, and R bracket P minus comma Q minus 1 red edges must be possible, because you can imagine this to be R bracket P minus 1 comma Q minus 1 plus R bracket P comma Q minus 1 minus 1 also, and then you must add 1 to it so that they are equal. And hence, after you have all these to be blue and all these to be red, this 1 must either go into this box or this box. And so either R bracket P minus 1 comma Q are blue, or R bracket P comma Q minus 1 are red. So, since the argument is similar, we can just consider one of the cases, and we consider that R bracket P minus 1 click has all blue edges connecting to V. Well, by the definition of R bracket P minus 1 comma Q, it must have either a P minus 1 click that is blue or Q click that is red. If it has a Q click that is red, it satisfies the condition that this number has a Q click that is red. If not, then if it has a P minus 1 click that is blue, because it is connected to V by only blue edges, this will form a P click that is blue. And this proves that this number click would have the following property, that there is either a P blue click or Q red click. And hence any number, Ramsey number, because it's the smallest one that fulfills this condition, it must be less than or equals to this number. And so, you can see how we have used the generalized pigeonhole principle to prove something in graph theory. You can strengthen the bounds by a few algebraic manipulation and some contradiction proof, and you can find that Ramsey numbers have been studied quite extensively online. I will not go into them as this is just a short introduction, but feel free to share anything you want in the comment sections down below. Thank you for listening, and I hope you have enjoyed this video.